Hello, my name is Jackie Russell. I'm a first year graduate student in the master's program for mathematics at Loyola University of Chicago. I am going to be making some of these web videos similar to some of the other videos you can find out there. I know there are a lot of different sources for these, from Khan's Academy to various other sources. But I'm going to be making some of these primarily just to validate for myself that I can effectively teach and describe some of these concepts, but as well as that, hopefully someone will be able to watch this and actually understand the concept better based on my videos. Uh, these first few videos I'm going to make are going to be pretty easy and pretty elementary as far as the concepts I'm going to go over. Hopefully I'll get into some more advanced things, some of the things I'm doing currently in school or have done in the past couple of years in school. But some of these first videos, like I said, are just going to be really easy things that someone maybe in junior high school or early high school would be working on. So with that being said, let me close my window so you don't have to look at me anymore. And let's go over some of these things. So you can see here that we have some circumscribed figures. So we have a square circumscribing a circle, and then we have a circle circumscribing a square. So the the thing that I want to figure out in this exercise is uh, what are the ratios? So what are the ratios of these circumscribed items? So in other words, uh, what is the ratio of this square to this circle, or to this circle to this square? And then what is the ratio of this square to this circle? So if I know the area of one, I can easily just use that ratio to check what the area of the other one is. And there's obviously easy ways to check what the area is even if you don't know that ratio, but the purpose of this is to try to find that common standard ratio of these things. So first off, what does it mean when something is circumscribed? Well, I mean, the real definition of it means that just something is drawn around something else. So, in a technical sense, this circle is circumscribing both this circle and this square. But this really doesn't do us any good as far as being able to easily understand some of these ratios, because this circle can be infinitely big, but it can only be a certain size once you're looking at it. It can only have a minimum size, because once you basically get a circle that passes through, if you think about it, passes through the square, then it's no longer circumscribing it anymore. So uh, obviously the minimum size that of a circle that circumscribes this square is one where the vertices of the square and the points of the corners of the square are touching the circle. Because if you go any further in, then those vertices are no longer inside the circle. And if you go out any, then obviously there's space between the vertices and the circle. So we're just looking at this minimum circumscribed circle, or this minimum circumscribed square, where if you go any further in, it's no longer inside the item is no longer inside the outer item. And then if you go out any, obviously you're getting bigger. So in both these cases, while the graphic might not exactly represent it, we are at the minimum circumscribed level for each of these. So in other words, this square is touching this circle at 4 points around the edge here, and this circle is touching this square at the 4 vertices. Now that's going to easily let us find uh, either the diameter of the circle based on a side of the square, or vice versa, or here we're going to be able to find the side of a square based on the radius of the circle or something like that. So let's look at this. So what we want to do is let's delete this. What we want to do is first let's look at this one here. So what is the ratio of a circle to its circumscribed square? So in other words, I want to know what the ratio of the area, what is the area ratio of the area of a circle to the area of its circumscribed square. So this area is always going to be the same, no matter if we make this square as big as we can and fit a really big circle in there, or make it really tiny. That ratio is always going to be the same. We'll see that in a second. So let's just look at an example using some numbers first. So if we look at this, let me make sure okay, so we're going to look at this circle here, and we're going to let's just set the radius equal to 2. Okay, so then in this situation, using these formulas here that you probably learned in, I don't know, 4th grade or 6th grade something, then we know that in this case that the area of the circle, so the area of the circle, getting some delay here, so the area of the circle equals pi times r squared, so pi times 4, and the area of the square then, well, because the square is circumscribed around this circle and we know these points are touching, if we expand this out to show, instead of having a radius, if we expand this out and make it a diameter, then we now know that the diameter of a circle is obviously just twice the radius, so the diameter now is 4. Well, because these points are touching the square, now this diameter of this circle is also the length of the side, one of the sides of the square. So then at this point we have the area of the square is the diameter, which is 4. Oh. So we have the diameter here, which is 4 of the diameter, d, and that equals 4. Now that also means that s down here equals 4. So the area of the square is just 4 squared, or 16, right? So what's the ratio then of the area of this circle to the area of its square? Well, we're going to put them over each other, make a fraction, and take the ratio. So you're going to have the ratio here. Let's go down here and do it. The ratio is equals 4 pi over 16. So the ratio is just pi over 4. So in other words, anytime you have a circumscribed square around a circle and you know the area of one or the other, then you can just multiply it by pi over 4 or 4 over pi, depending on which one you know, and you can easily get that value. So obviously, looking at this example, I know the area of the square is 16. I know the ratio is pi over 4, so I multiply 16 times pi over 4, and I get 4 pi. So the numbers work out. So let's look at that just really quickly in a generic form. So if we take out a number and just call this radius r, then the area of the circle again is just, down here we've got pi r squared. Now this diameter then is just twice the radius, or 2r, right? So the diameter of the circle then becomes diameter. Oh. So the diameter here equals 2r. So then what we have here is we have the area of the circle equals pi r squared. The area of the square equals Well, the diameter is 2r. That means the side of the square is 2r. So we're going to square 2r. So that's going to be 2r all squared. Well, that's just 4r squared, right? So again, put these things over each other. We're going to have the ratio then. The ratio is pi r squared over 4r squared. And the r squares cancel out. So again, we end up with pi over 4. So using any arbitrary radius here, not just using some number that we chose, we still end up with pi over 4. So we know that this is the ratio of this is always pi over 4. So the answer to this question is pi over 4. Okay. So now let's look at the other side of the picture. Oops. So in this scenario, if we know the radius of the circle, so let's say the radius here, well, I mean that doesn't look like it helps us much, right? But the radius also, if this is the center, which it might not, I might not have put it right in the center, but the radius also goes like this, right? So if you think of it this way, then the radius, if you extend this out to the diameter, then you're going to have, and that's obviously not a straight line, you're going to have basically a diagonal that cuts through that square and separates it into two congruent triangles, 45, 45, 90 triangles. So again, if we can easily set some arbitrary radius here, and we can easily see based on these items what the ratio is. So let's change this a little bit. Instead of looking at the ratio of a circle to the area of its circumscribed square, we're going to look at the area of a square, ratio of the area of a square to the area of its circumscribed circle. So again, let's say that this radius here is r. Oh, I'm going to learn more to make sure my pencils and stuff are changed correctly. Let's make this radius r. Then this diagonal across this square is then 2r. Okay. Now we know then at this point that the area of the circle is pi r squared, but we're going to have to do a little bit of algebra with either the Pythagorean theorem or some formulas that we remembered about 45, 45, 90 triangles to get the area of this square, because we don't have the length of the side yet, we just have the length of the diagonal. So let's just look at it based on the Pythagorean theorem, thinking that we don't remember the 45, 45, 90 rules. Since this is a square, these sides are the same. So whereas the Pythagorean theorem says a squared plus b squared equals c squared, a squared and b squared in this situation are the same. So we're going to basically have a squared plus a squared equals 2r squared. So that ends up being a squared plus a squared equals 2r squared. So then we end up with 2a squared equals 4r squared. And then we divide by 2, we get a squared equals 2r squared. So what is a then? Well, a is then the square root of 2, because we're going to take the square root of both sides. A is then the square root of 2 times the square root of r squared, which is just r. So this equals a. So the sides of this square, if the circumscribed circle has a radius r, the sides of the square are each the square root of 2 times r. See that? So then the area then of the square is square root of 2r squared. So the area of the square then, area of the square is the square root of 2r squared. Well, that's just 2r squared. Okay, so we have the area of the circle, pi r squared. We have the area of the square, 2r squared. So we want to know the ratio of this square to this circle. Well, we do the same thing we did before. Let's put the area of the square on top of the fraction, 2r squared. Put the area of the circle on the bottom of the fraction, pi r squared. These cancel out. So the ratio here is 2 over pi. So let's fill in some numbers here. Let's say the radius is 1. Okay. Well, then the area of this circle, if the radius equals 1, then the radius of the circle is just pi, because pi times r squared is 1, right? Well, then the diameter of this circle, of the square, is 2, and then the area of this circle is going, so if r equals 1, then this diameter is going to be 2. These sides are going to be the square root of 2, because remember we said that it was a square root, the a equals the square root of 2 times r. Well, r is 1, the sides are square root of 2. Then that means this area is the square root of 2 squared, or 2. So the area of the square in that case, so this is the area of the circle. If r equals 1, the area of the circle equals pi. The area of the square equals 2. And then you can easily see that the ratio is 2 over pi. Now we can fill in some other numbers, but that should suffice to explain, to show you that the generic form really shows you that ratio is going to be the same no matter what, because we chose an arbitrary r. But I just picked one of those, one number, just to show you that it does end up looking like that. So let's do one other thing real quick. Erase some of these items here. Wow. Okay, that's not going to work very good. All right. We'll just leave that there. So the last thing I wanted to do is just another simple little exercise. So what is the area in this situation of, I'm going to highlight something. So what is the area of that pink area there? And if you think about it, that pink area is really the area of anything inside that square that's not inside that circle. So it's just going to be an easy subtraction problem. Now, again, let's use an arbitrary r. So the area of the square using r equals, the radius equals r, then the diameter again is 2r, side of the square is 2r, then the square area itself, in that situation, I'm going to keep the pink one here, the square area is 4r squared, and the circle area in that situation is just pi r squared, right? So then the area of this pink area is going to be the area of the square minus the area of the circle. So then the pink area, see, the pink area here is equal to 4r squared minus pi r squared. Easy, right? So let's just substitute in a number here real quick. So if the radius here is something easy like 1, then the area of this pink filled in area is going to be, we'll just substitute in our formula here, 4 times 1 squared is 4, pi times 1 squared is pi. So then in this case, if r equals 1, then the area of this pink shaded area is going to be 4 minus pi. Easy. Now, we want to switch over here and do something similar in the other one. it might be a little more difficult. Actually, it won't be. It's going to be the same type of thing where we're going to find the area of the circle, subtract the area of the square. If we wanted to find the area of, for example, that shaded area right there, that's going to be a very similar thing. We're going to take the area of the circle, we're going to take the area of the square, subtract the two, and we can easily find a formula similarly to this. All right, so that is my first video attempt. I hope that everything I said was clear, and everyone that sees this understands everything. If you have any questions, feel free to comment. Otherwise, look for some of my other videos soon.